Hello students, here we're with the Integrator exam review problem. This problem here gets you to think about how an integrator works when it's made with an op-amp. So before we actually start, let's look at the derivation of the formula that shows you how to calculate the values for an integrator circuit. So we have, by the golden rules, the current that is going to go in through this is going to go out through that by the action of the amplifier. That is, the amplifier will produce a voltage sufficient to draw current through the capacitor in order to maintain this point here at the same point as there. That is, to make this a virtual ground. So remember, this then is always at 0 volts. For this kind of a setup, because this is fixed at 0 volts. So that means that if I have some input voltage and I have some output voltage, they have to be related as follows. I have an input voltage here, it's going to send a current through this resistor. So the input current is going to be equal to the input voltage divided by the resistance. That's also going to be equal to the capacitance times the rate of change of the voltage at the minus terminal minus the voltage at the output. And since this is equal to 0, this is simply given by minus C times dV out by dt. So that means that the input is related to the output by Vn over minus Rc is equal to dV out by dt. Or the output as a consequence of the input is simply the integral of this equation. So the output is equal to 1 over Rc times the integral of the input voltage as a function of time, integrated over time. So this formula here comes directly from the golden rule that the amplifier does what is ever necessary in order to maintain the plus and minus inputs at the same voltage. And it also comes from the golden rule that there's no currents actually going into the inputs of either amplifier, either input of the amplifier. So now we're imagining that we are going to have an input of a 1 kilohertz square wave. And we're going to get a triangle wave with an amplitude of 5 volts peak to peak on the output. So let's sketch this so we can get some sense as to what this looks like. So the input looks something like this. Here's the input voltage as a function of time. And I'm going to have a square wave. I'll just have it go positive starting at time equals to 0, and then it will go positive for a while, and then it will drop down to the negative, and then it will come back to the positive, and then it will go down to the negative, and so forth. The output is going to be as follows. Remember, this is the integral. So every time I advance, the area of a little piece is going to add on to whatever the output is, and it's going to add on with a minus sign. So if I was imagining starting from 0, then the actual output would look something like this. It's going to go down. As each piece is added on, it's going to increase the area under this curve, and that's going to make this grow to some negative value. Once it flips sign, then the current reverses and the capacitor is discharged, and it goes back towards 0. So if this is a symmetrical sine wave, or a symmetrical square wave rather, you're going to get a triangle wave which is always below ground if I start from 0. So I would have a triangle wave that looks kind of like this, where these points represent the changes from positive to negative on the square wave. So you can see by this construction that the peak value, that's V peak positive, and that's going to be minus V peak. The peak to peak is twice that. Whereas on the output, that amount there is the peak-to-peak voltage. And the full period of the square wave is this distance. So this here is t over 2. Okay? So now if we integrate our square wave, assuming it's a constant up to this point, what we'll have is that the output is going to be equal to minus 1 over RC times the integral of a constant, which is just the peak value, times dt between 0 and t over 2. And this is basically just minus 1 over RC times V peak, evaluated between 0 and t over 2, where t is the time. So that's just minus t times V peak over 2 RC. And that's the output voltage. So if we go up to this point, this output is equal to the peak-to-peak voltage. So our formula that we use to calculate looks like something like that. V peak-to-peak out is equal to minus T times V peak in over 2 times RC. So our goal is to find some values of R and C that accomplish this. So I solve this equation for RC, and I will get minus T times V peak in over V peak to peak out, and a factor of 2 in front. So the sign, remember, this basically tells us that our peak to peak voltage is negative. So I can ignore the sign and just plug the values in. I'm going to have for this time, this is a 1 kilohertz wave, so the period is equal to 1 millisecond. And the peak voltage is half of the peak-to-peak voltage, so it is a 1 volt peak-to-peak square wave, so this peak voltage is 0.5 volts over 2 times V peak to peak out, and the output is 5 volts. So this sets our value of RC, which if you plunk the numbers in to your calculator, you get that RC is 0.05 milliseconds. So then you just have to pick a value of R and C that gives you this time constant. There's a wide range of values. What I like to do is to choose the capacitor first, since the numbers of types of capacitors are smaller. So I will choose capacitor of equal to 0.01 microfarads, and that gives a value for R of 5,000 ohms, and the nearest one that's that is 5.1 K. So that R and this C would give me what I want.